Hello students, welcome to chapter 2. We're going to be talking about basic atomic structures, molecules, chemistry, stuff like that. So organization of matter consists of elements, atoms. So we know the periodic table. These are all the pure substances. The elements, right? So pure substances that cannot be broken down into similar substances or simpler substances by ordinary or chemical or physical techniques, right? We know the basic elements: hydrogen, carbon, lithium, sodium, beryllium, all of those. All matter in our universe is composed of elements and combinations of these elements. So we have 92 different elements naturally occurring on Earth. Anything beyond that can be synthesized in a laboratory or artificially synthesized. I'm sure a lot of you can name a lot of these elements. I cannot. I am not a chemist. But we have the simple ones that are known for life. We have oxygen, hydrogen, carbon. We also have potassium, nitrogen, phosphorus, calcium, magnesium, iron, sodium, zinc, copper. So a lot of these things are found in life, and then a lot of these things are found in other places, right? So life and non-life. Things that we've discussed earlier in the first chapter when we talked about ecology-based things. So seawater contains a lot of oxygen, and then hydrogen, some chlorine, some sodium, some magnesium. We can also say that humans have a lot of oxygen, right? But we also have a lot of carbon. We also have a lot of hydrogen, nitrogen, and then some calcium, some phosphorus, and then what you call trace elements, like chlorine, magnesium, iron, and iodine. Other things like pumpkins, plants, right? They also have a lot of oxygen. They also have a lot of hydrogen in them, right? Because they would contain more water than us. They need carbon, potassium, nitrogen, phosphorus. They also contain some trace elements. And then the Earth's crust, which is more stone, again contains a lot of oxygen, but not as much as, humans, pumpkins. But then it contains a lot of silicon, right? Because it's rock. And then it contains aluminum, iron, calcium. So definitely different elements throughout different things, but they're all containing the same type of elements. So we have 25 key elements in living systems, right? Four elements that make up more than 96% of the weight of living organisms, right? These are carbon, hydrogen, oxygen, and nitrogen, right? These are things that make up our living systems that just can encase all of our cells, all of our systems, and everything. We have 7 elements that make up about 4%, right? So 96, 4. That's calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. These, if you have a deficiency of these, can cause a lot of symptoms that can otherwise cause a lot of problems in your system. Chlorine maybe not so much, but you know, it depends. Now, there are trace elements that can make up less than 0.01%. So if you have 96 plus 4, that's about 100%. But these trace elements can make up what's remaining from that. So iodine is a trace element, right, from that. One of your attendance assignments, what I'd like you to do is name a few more trace elements for me that might be found in living systems. Okay, atomic structures. You should know this, but I'm going to go over it anyways. Atomic nuclei, right in the center of the atomic nucleus, is protons and neutrons. The number of protons is the atomic number that identifies the nucleus, or identifies the element. This nucleus is surrounded by these fast-moving electrons. Usually, I'm not going to say this, but usually the number of electrons is the same as the number of protons if it is stable. If it is a stable molecule. So if you have one proton, you're usually going to have one electron. If you have 6 protons, you're going to have 6 electrons. Now, that's almost never true, but it's something that it's preliminary. I'm gonna tell you this now. So a neutron and a proton have almost the same exact mass, and it's about 1.66 times 10 to the negative 24th grams. You don't really need to know that number. What you're going to need to know is basically just that it's called 1 Dalton. It's 1 Dalton of mass. Atoms are assigned a mass number. And this is based on the total number of protons and neutrons in the atomic nucleus. So if you have 6 protons and 6 neutrons, that's going to be 12. Electrons don't really contribute that much mass. It's about it's a really, really small amount of Daltons. Distinct forms of atoms can change the number of neutrons in a nucleus. And these are called isotopes. So if you have the same number of protons, but if you have the different number of neutrons in the nucleus, that's called an isotope. And this can change the reactivity of that atom. So let's say that you have a hydrogen atom, and it usually only contains 1 proton. It doesn't have any neutrons in it whatsoever, but it has 1 proton in it. Let's say you add a neutron in there just randomly, right? Then it becomes deuterium, or is it called 2H, right? That changes the mass number, right? So all of a sudden it changes from 1 mass to 2 mass. Right? Suddenly it becomes twice as heavy. That changes the reactivity of this atom. And even so, if you get 2 neutrons in there, it becomes tritium. That triples the amount of mass in this atom. It almost changes it from 1H to 3H. It almost changes it to a molecule. But it's an atom. So organisms can use hydrogen or the carbon isotopes to use this in chemical reactions. So let's say that you have 6 protons and 6 neutrons in a carbon, but it gains an extra neutron, right? This extra neutron gives it to C13 instead of C12. So this changes it somewhat, giving it an extra reactivity. And it can change it also to C14, giving it an extra reactivity. Now that can bump down almost to where it's unstable, it can break down somewhat, giving off particles, and this is called radioactivity. Nuclei of some isotopes are unstable, they can break down, and that's called decay. That isotope transforms. Radioactive decay is called radioactive isotope, and that radioactive isotope, that radioisotope, and that's called radioactive decay. Sometimes that decay can transform that unstable radioactive isotope into another element. So 14C, right, can change that type of compound, that type of element into kind of like a nitrogen. With its mass number, it changes it somewhat into reacting like a nitrogen. So we talked about radioactive decay. So as it decays, it actually decays at a steady rate. It's unaffected by any type of environmental condition or any type of chemical condition. We can actually track it depending on time. And this is called radiometric dating. Radiometric dating uses radioisotopes and that decay to estimate the age of organic material, fossils, rocks that contains these radioisotopes. So you can use trackers or tracers. So those radioisotopes such as C14, P32, you can use S35. And you can see as it stabilizes how much of one type of radioisotope is found in a fossil, is found in an organic material from the day that they died to the day that you found the fossil or the organic material. And you can see how far back that was. And that's just a continual rate, right? And you can see, well, this is approximately this long, depending on how much radioisotope is left in that material. So you can do this with rocks, depending on how much uranium is left in the material to turn into lead, or you can do this with organic material, depending on how much C14 is left that turns back into C12 or C13. So when we talk about compounds, these are elements or atoms that have bound together, right? When atoms bind together, they're called molecules. And when those molecules bind together, they're different atoms that bind together, they're called compounds. So these compounds have molecular names written as a chemical formula using standard symbols, right? Chemical formula, empirical formula, these are things that you might find in the lab that we did Monday, I think, yeah. Elements such as CO2, or this caffeine molecule over to the side. So these molecules have component atoms which are different. Carbon dioxide, which is a compound. They have chemical and physical properties, typically distinct from those other atoms or elements. Typically, if you have like hydrogen and oxygen, which are completely different from each other, if you have them in gas form, they're highly flammable, right? But if you put them together, they're not. They're water. That's water. So they're completely distinct, separate, but if you put them together, they're distinct as well. Usually ionic bonds are between a metal and a nonmetal. You're going to have one that gains a valence electron and one that loses a valence electron. You're also going to have metallic atoms, such as calcium, magnesium, all these other ones that can lose 2 or 3 electrons. These can form cations that join ionic bonds. These aren't too important, but you can, put them together. Ionic bondings have 3 features, right? They have an attractive force that converts a greater distance than any other chemical bond, right? Their attractive force extends in all directions, and they can vary in strength depending on the presence of other charged substances. So if you have one positive force that needs to attract a valence electron and one negative force that is giving a valence electron, it's going to try to give that valence electron over to that positive force. Then we have covalent bonds, sharing a pair of valence electrons rather than gaining or losing them. So these will share those valence electrons. So the valence electrons are on the outside shell of those atoms, in case you didn't get that. The shared orbitals will form that bond, right, at discrete angles. So usually it'll be at an angle, and then there will be another angle, and then there'll be another angle. There'll be really distinct three-dimensional forms here. And you can see those three-dimensional forms with these molecules. So this right here is actually a molecule of cholesterol. So electronegativity is the measure of an atom's attraction for the electrons it shares with the chemical bond of another atom. And you can see how that might fit in here. How these are formed can kind of indicate how the shape is. It'll push the shape out depending on how the electronegativity pushes. I'm going to explain this weird. So it'll push the shape out depending on how the attractive force goes against the atoms in the molecule. So it's like a magnet, right? If you have one side that is negative, one side that is also negative, right, it'll push against each other. Or if one side is positive, the other side is positive, this side is positive, that side is positive, it'll push against each other depending on how the attractive force or the, in this case, disattractive force is. So covalent bonds differ widely and the sharing of valence electrons, depending on the difference of electronegativity. Also, polarity. If you have a nonpolar covalent bond, all electrons are shared equally. So all of the electrons are just shared throughout its route, throughout the molecule. But if you have a polar covalent bond, the electrons are pushed against one side or pushed against another side. And if you take water, for instance, you're going to have hydrogen pulled to one side, and then the electrons are pushed to the other side, because hydrogen is positively charged, right? It has more protons in it, and then the oxygen is going to have its electrons pulled to the other side. So the atom that attracts the electrons, more partially negative, is called sigma negative. The atom deprived of electrons is sigma positive. And you can see that on the diagram. Because of this positive negative pull of polarity, you get what's called hydrogen bonding. So this attraction between this partially positive and this partially negative pull can share this almost bond between this between these sides. So you can see here, hydrogen, you have a positive end, and then you have over here nitrogen that has negative end, right? So hydrogen over here is kind of pulling against this nitrogen, and it shares a bond here, even though it's not within the same molecule. So it's bonding, even though it's kind of weak. If you get a whole bunch of these, it's collectively strong. Let's say that you have a whole bunch of string. If you just had one string, you could pull it apart, but if you had a whole bunch of string, you wouldn't be able to pull it apart. It's like having a phone book. You wouldn't be able to rip open a phone book, but you can tear a piece of paper. So hydrogen bonds can stabilize three-dimensional large structures, such as proteins or DNA molecules, right? But you can just as easily slap your hand down on water and push your hand down through it. Other properties of water can include high specific heat, right? You're going to have a lot of bonding, so you have to break those bonds, right? Usually a calorie of heat is the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. Heat of vaporization, you're going to have 586 calories per gram. That's about its heat that you have to vaporize. So it has to break loose from its liquid form to get into gas. Other things, cohesion. That's water to be able to stick to itself. That's hydrogen bond lattice. Water to be able to stick to water. That's cohesion. Adhesion, it's water to be able to stick to other things. Okay? Like the tubes of a wall, the glass, glass, or other things. Surface tension. A film of a liquid causes the attraction of particles in the surface layer. If you have like a bulk of a liquid, and if you put something on top of it and it kind of just floats there, that's the tension of the surface of water. And that's kind of what's helping the spider be able to float on the water. If you have the lattice of liquid water, it's basically just kind of floating around. You just have these bonds kind of unmotivated. You can kind of flip through them. But if you have ice, what they do is they'll crystallize, they'll form together, right, into more three-dimensional structures. So it's harder to push through that, which makes it, much more rigid. Other bonds that you can that we can go through. Van der Waals forces. These are weak forces developing over just very short distances that develop between nonpolar molecules. Temporary, between positive and negative charges. Just charged regions between those molecules. Formation of many bonds between those molecules. So in this gecko has just very small hairs that has charged nonpolar regions in those hairs, but it has so many of them that it can stick to almost any substance that it can find. The same thing goes with proteins. Okay, shape of a large molecule such as a protein, it can just temporarily get a charged region and bind to a substrate and then just use it to do its work. Molecular shape is crucial because it determines the function of a molecule, right? Without that molecular shape, it wouldn't be able to bind. It wouldn't be able to use that charged function. So, cells function between the interaction of its substrate. It's similar to a lock and a key. In biological systems, chemical reactions are accelerated by these proteins, by these enzymes. So it has to be able to know what type of structure it is, and then the substrate can come in, bind to it, and then release it. Some drugs, some medications may mimic the shape of these natural molecules so that they can block or interfere with the interactions of them. Or it can just do its job. Any other type of chemical reactions, atoms or molecules, these are called reactants at the beginning, and then those leaving the reactions are called the products. Right? So if you have the enzyme, at the beginning it's called the reactant, at the end it's called the product. The arrow shows the direction of the chemical reaction, and we should all know what the chemical equation is. And it should be balanced, right? Overall reaction of photosynthesis is here, and it's balanced. Other things, phospholipid bilayer. This is a very important system because it encompasses all the cells inside any living system. We'll go into a lot more detail with this later, but I just want to introduce the subjects. So phospholipid bilayers consist of lipid molecules with dual polarity, right? So on one side it has a non-polar side, and the other side has a polar head, right? The polar head is facing the outside where the water is, right? Because polar meets polar, right? And then the non-polar side fits where all the non-polar tails are. So all the non-polar tails are fitting together. So it's a bilayer, so all the non-polar tails are together, and all the non-polar heads are facing the outside where the water is, or where the aqueous solution is. Next is acids and bases. So you should know what an acid and base are. Acids are proton donors. This means that they release hydrogen atoms when they're dissolved in water. You should know that. They increase the hydrogen concentration when they're dissolved in a solution. Okay. Bases are proton acceptors. They reduce the hydrogen concentration of a solution. That means that some of them release a hydroxide ion when they're released into a solution. And usually release a cation as well. Some type of cation, including sodium, magnesium, something like that. Okay. Acidity is usually measured using the pH scale. Now, that's ranging from 0 to 14. That doesn't also mean that it goes beyond that point. It's just usually measured at that point. But this is based on a logarithm using the number of hydrogen atoms in a solution. Okay? So, that's negative log of 10 of hydrogen ions. Human blood is about 7.5, depending on what it is, but that's not... usually you need a buffer of some kind. Okay? So each whole number on the pH scale is 10 times greater or less than the next number. So if you have 7, if you have 6, it's 10 times less than 7. If you have 5, it's 100 times less than 7, and so on and so forth. Right? So, keep that in mind whenever you're looking at the pH scale. So, whenever we talk about buffers, these are things that compensate for that pH by absorbing or releasing those hydrogen ions. Okay? These compensate basically by keeping that pH scale at a specific pH. When hydrogen ions are released in excess, buffers combine with those hydrogen ions and remove them from the solution. If the hydrogen ions decrease greatly, right? If it starts to decrease a lot, the buffers will release those hydrogen ions, right? Making the pH come back to what you would consider that normal pH. Most buffers are weak acids or bases that dissociate reversibly in water solutions to release or absorb hydrogen ions or hydroxide ions. Carbonic acid bicarbonate buffer system usually buffers blood pH. So yes, blood needs some buffer solution. We ourselves do have a buffer system in ourselves that allows for some levels of buffering. And that just happens whenever we eat. Sometimes our system does have some buffering. In a reversible reaction, carbonic acid, a weak acid, dissociates into bicarbonate ions and hydrogen ions. So this is just the formula that goes back and forth with it. And then this is the graph that kind of shows you how the buffering system goes in your blood. So if you have a normal pH, you want it to kind of remain at that pH scale, but your buffering capacity, this is your percent of buffer in the form of H2CO3. But your buffer, it kind of wants it to remain at that pH scale. So yeah, it keeps it at a normal pace within your system, so it doesn't go over or under that normal blood pH. Make sure that you do that attendance assignment, okay? And then make sure that you're doing the labs, and I will see you later.